Now we are going to see this numerical. The numerical is as shown in figure. And we have to calculate the velocity of B and D, angular velocity of CD, linear acceleration of B and D, and angular acceleration of CD. Now to begin with this numerical, you have to draw the space diagram by assuming some suitable scale. So this is the space diagram which is drawn as per the scale considered for the space diagram. 1 centimeter equal to 100 mm. Also, we have calculated the magnitude of crank, velocity of crank, that is 0.628 meter per second, right? So after drawing this space diagram, as we know, to begin with the velocity polygon, we must know the direction of crank. Here the direction of crank is anti-clockwise. It is given and velocity is calculated for the crank is 0.68. So after knowing the magnitude and direction of first link, we can begin the velocity diagram. So first locate the pole. Poles are the fixed point from your space diagram. So here the fixed point is O. So we are locating pole as a O in the space. Before that, we have assumed the velocity scale of 1 centimeter equal to 0.2 meter per second. Now velocity vector for the first link OA must be drawn from the one of the point O or A should be available here. So OA is available. We are going to draw a perpendicular line to OA in this direction because the crank is rotating in the anti-clockwise direction. So from O, draw a vector perpendicular to OA in downward direction. Here it is. The magnitude of that is already calculated. As per scale, we have drawn this line perpendicular to OA. The end point is A, and this is the vector VAO, velocity of A with respect to. Then next link is the AB. This is A, and this point is B. The velocity vector for AB is a perpendicular line you have to draw in the velocity polygon from where either A or B point should be there. So we are having A point. So that perpendicular line to AB is drawn from the A point, this point. So let's draw a perpendicular line to AB from the A. So this is the perpendicular line to AB. After finishing the perpendicular vector of AB, next link is a B, slider B. The velocity of slider B is a parallel line to the line of stroke. The slider B is sliding in horizontal manner. So line of stroke of this slider is horizontal. So draw the horizontal line from the pole O, which cut the previous vector and it intersect at B. So we got the velocity of B by the horizontal vector, that is the slider velocity, and velocity of B with respect to A is also known here. After completing this, until and unless you are not locating this C point, you cannot move to draw the further vectors. So locate the C point by this formula, small ac divided by AB equal to capital AC divided by capital AB. From there, we will get the AC because this AC is known, the capital AB is known, capital AC is known. The small AB, you have to measure from this vector line, measure this distance A to B. That distance you have to use as a AB. So you will get the AC in centimeter. and that you have to mark on the AB vector because C point is appearing on the AB link. So similarly, your C point will come on the AB vector. So we have located the C point by using this formula. After getting the C point, next link is a CD. The CD, the velocity vector will be a perpendicular line to CD. But you have to draw this perpendicular line in this vector diagram. From where to draw? Either C or D point should be available here. So we are having C point. Draw a perpendicular from C to the CD link. This is the perpendicular to CD and this is the velocity of DC. After drawing that CD vector in the velocity polygon, you are having a next link is the slider D. Slider D is having its line of torque in vertical manner. So as we discussed previously, the velocity vector of slider is drawn from the pole O. Here the line of torque of the slider is vertical. So draw the vertical line from O which cut the previous vector of DC link. And that point will be the D point. So here ends the velocity diagram of this. Now after completing the velocity diagram, we are about to draw the acceleration diagram. To begin with the acceleration diagram, we have to prepare this table. Table contains the link, length of the link in meter, velocity in meter per second, the radial component of acceleration and tangential component of acceleration. So whatever the different link that you have to note in the link column, OA, AB, CD. We are not included here sliders. The link lengths given are written in the meters. Velocities magnitudes are calculated by using this vector diagram. To calculate the velocity of any link or sliders, you have to just measure that vector, multiply with the velocity scale, you will get the velocity values. So these velocity values are written in the velocity column. Now radial component of acceleration of all link. The radial component of acceleration of all links is given by the velocity square divided by length of that link in meter. So the radial component of all the links are calculated here. Now by knowing the acceleration magnitudes of different links, we are selecting a scale. So we have selected here scale 1 centimeter equal to 0.2 meter per second square. To begin with the acceleration diagram, you have to start with the locating the poles. So locate the pole. Pole is the O. Remember, we have to use the dash with the alphabets. So O dash is the pole. Now very first link is the OA link. This OA is, we are considering rotating with the uniform speed. So it got only one component of acceleration, that is the radial component. Radial component, it is also called as centripetal component. It always act toward the center. Center of this OA link is O because it is fixed point. So radial component act toward the center. So radial component of OA is in downward direction, which is the parallel line to the OA. But you have to draw this in the acceleration diagram here, which is in downward direction. From where you have to draw either O or A point should be available. So already we have the O point with us. So from O, draw a parallel line in downward direction to represent the velocity vector of OA, which is the parallel line to AO. So this is the parallel line to OA in the downward direction, which represent the radial component of OA. The end point is A dash. So radial component of AO is here in front of you. Now next link is the AB. This link AB. This AB got the two components of acceleration. First one is the radial, which is the parallel acceleration component to that link. But direction, you have to remember that the direction always toward the center. Which is the center for AB? The A will be the center. This will be the center. So centripetal component of AB will act, or radial component, also called radial component of AB, will act in the direction of center. So this line which is parallel to AB, which we are calling as a radial component of AB, is going toward the right up. And you have to draw this in this acceleration polygon from the either A or B point which is available. Now A point is available here. So draw this parallel line to AB in the upward right direction of magnitude 0.243 as per the by using the scale. So this is the radial component of AB. Also, this AB link will have another component of acceleration, and that is the a perpendicular, or it is also called as tangential component of acceleration. We are writing that as a AT, tangential component of AB, which is a perpendicular line, to link AB. Where your radial component ends at x dash. From that point, you have to draw a perpendicular line to AB. So let's draw the perpendicular line to AB that represent the tangential component of AB, which is shown here. This is the tangential component of AB. Now after finishing this, the next link is the your slider B. The acceleration of slider B is a parallel line drawn to the line of stroke. So line of stroke of this slider B is horizontal. So draw the horizontal line from the pole O dash. And this will cut the tangential component line at this point. And this point will be the B dash. And this line represent the acceleration of slider B. Now after finishing this, you have to draw the net or resultant acceleration of AB. I said that you have to observe that radial component starts at the A dash. And the tangential component ends at the B dash. So join these 2 points by a solid line that represent the net or resultant acceleration of AB. So this is the resultant acceleration of AB. Now after finishing that, until and unless as per your velocity polygon, also here also you have to locate the C point on AB vector, A dash B dash vector. Again, to locate that C point on this AB vector, you have to use the equation A dash C dash divided by A dash B dash equal to AC divided by AB. AC, AB are given in numerical. These are the lengths of that link. A dash, B dash, you have to take from this, measure the length of this AB vector. You will get the A dash, C dash in centimeter. So you are getting A dash, C dash means you have to look at the C dash point from the A dash, So we'll get the C dash here, which we have located by using the above formula. So after locating C dash, it is easy now to draw the velocity acceleration components of this CD. This is the CD link. For CD link, two components of acceleration will be there. One radial and another one is a tangential. As we know, first way to locate the radial component of CD, first identify the center of CD. As I said that center of CD is the C. Always you have to take the previous point. Previous point of CD is C. So centripetal component acts in the upward direction. So the line which is drawn parallel to the CD in upward direction represent the radial component. But this line you have to draw in this acceleration polygon. From where? Either C or D dash should be available. So we are having C dash. Draw a parallel line to CD in upward direction, which represent the radial component of CD. So this is the radial component of CD. Now another component of acceleration for this link CD is the tangential component, which is perpendicular. So tangential component to CD is drawn where your radial component ends. Your radial component ends at the y dash. Draw a perpendicular line to the CD from y dash. So this is the tangential component of CD. Now after drawing this tangential component, next link is the D. D is having line of torque vertical. So for a slider, the acceleration component is a line drawn parallel to the line of torque of the that slider. From where you have to draw? You have to draw this from the pole. Our pole is O. So line of torque of the slider D is vertical. Let's draw a vertical line from the pole which represent the acceleration of slider D. Now, as usual, for CD link, where is the net acceleration? What I said where you have to observe where the radial component of CD start. The radial component of CD start here at the C dash, and tangential component ends at this point. Join these 2 points that will give you the resultant acceleration of CD. So this is our total acceleration diagram for this numerical. Now we'll go for the calculations. One calculation of velocity and one calculation of acceleration I will explain here. If you have to calculate the velocity of slider B, what you have to do? You have to just measure the vector OB, multiply with scale, that will give you velocity of B. Now, any case, if they ask you find out the angular velocity of any limb, let's apply this angular acceleration of AB. So angular acceleration of AB equal to velocity of AB by above formula divided by radius of link AB. So velocity of AB is nothing but vector AB multiplied by velocity scale divided by your AB length. This will give you the angular velocity of that particular link. So this is the sample calculation of velocity, the sample calculation of acceleration. Let's consider they are asked to find out the acceleration of slider D. Now to find out the acceleration of slider D, you have to measure that this is the D dash. You have to measure O dash, D dash vector, multiply this with the acceleration scale, and that will give you the acceleration in meter per second square. This is the linear acceleration. In same formula you can use for the any link to find out the acceleration. Similarly, if they ask you have to find out the angular acceleration of link AB. So we know the tangential formula of acceleration is given by alpha AB multiplied by link AB. So alpha AB is 80 AB divided by link AB. So how to find out 80 AB? 80 AB is you have to Take the vector distance a dash b dash, multiply this with the scale of acceleration divided by AB length in meter. That will give you the angular acceleration. In this way, you can solve your any calculations. So this is the acceleration diagram for the mechanism which contains the 6 links. Thank you very much.